So, respected professor and respected our dean, Dr. Abhay Dharamsi sir, principal of PIPR, Dr. G.S. Chakramurthy sir, principal of School of Pharmacy, Dr. Lalit Lata Jha ma'am, my colleagues and participants of today's webinar, and my dear students. Very good morning to all, one and all. Today, we are having the webinar on the topic of basics of stereochemistry. One of the renowned personality is Dr. Dinesh Thakkar sir. So first of all, let me introduce our speaker. So Dinesh Thakkar sir has currently working as an associate professor in AR College and GH Patel Institute of Pharmacy. Sir has completed the BPharm in 2003 from AR College of Pharmacy, and he has completed his postgraduate from the Banaras Hindu University, and sir has published several books and several articles in reputed journals and national and international journals. So now I would like to request sir to please proceed the session.
Thank you, madam. Thank you, Nidhi ma'am. And thank you all the Parul University family for inviting me for this guest lecture. So, shall I begin, ma'am?
Yes, sir.
Okay, thank you, ma'am. Okay, so today's my topic is on stereochemistry. So, before beginning with that, we have to learn about the isomers. What is a isomer? The isomers are the compounds which are having a same molecular formula, but they have a different connectivity or different arrangement in a of atoms in a space. Say for example, we have a molecular formula of C2H6O. Okay. Now, for this molecular formula, two compounds are possible. The one is a ethanol, another one is a dimethyl ether, or we can say it's a methoxymethane. Okay, this is the structure of a ethanol, and this is a structure of a methoxymethane. Now here we can see that the connectivity of atoms is different. Here initially we have a two carbons which are attached to a oxygen as a third atom. Here the oxygen is sandwiched between the two carbons. Okay. So for this same molecular formula, we have two possible compounds. Okay, so both of these compounds can be considered as a isomers of each other. The another example for this molecule, the C5H14 formula is pentane, isopentane, and neopentane. These are the structures of the particular compounds: N-pentane, isopentane, and neopentane. Here we can see that in N-pentane, the carbon chain is straight, while in isopentane we have one carbon attached in a branch. Sorry. In a neopentane, we have a tertiary carbon, so a quaternary carbon, which is attached to a four other carbons surrounding that. So in all these molecules, the connectivity of carbon atom is different. So all of these compounds are said to be isomers of each other, which have a same molecular formula but different connectivity in structure. Now this is the classification of isomers. The isomers are classified as constitutional isomers and stereoisomers. These stereoisomers are further classified into enantiomers and diastereomers. The diastereomers are further classified into a configurational and cis-and-trans diastereomers. Okay. So we have already studied about isomers. Isomers are the compounds which have a same molecular formula but different connectivity of atoms. Okay. Now starting with the constitutional isomers. So constitutional isomers, as I have given the example earlier, they are the isomers which are having a same molecular formula but different connectivity. Okay. Here in an isomer, there could be a different arrangement of atoms in a space also. That is possible in enantiomers and diastereomers. That examples will be taking later on. I have here given the examples of constitutional isomers only. Okay, isomers are again classified into a constitutional and Stereoisomers. So here in this examples, I have given only examples of constitutional isomers. We'll be taking the examples of stereoisomers later on. So these are the constitutional isomers. Another example is that we have a molecular formula of C3H8O. For this same molecular formula, three molecules are possible. The first one is, we can say it's methoxyethane. Another one is a 1-propanol, and another one is a 2-propanol. Here also you can see that the connectivity of atom is different. Okay? All of these molecules, they are having the same molecular formula, that is C3H8O, but their bond connectivity is different. Here the hydroxyl group is attached on a first carbon in a linear carbon chain. Here the hydroxyl group is attached on a second carbon of a linear carbon chain. Here the oxygen is incorporated in between the methyl group and the ethyl group. So all these molecules are having a different connectivity of the atoms. So they all are considered as a constitutional isomers. The stereoisomers, they are the compounds, or we can say they are the isomers with the same connectivity. The atoms are connected in a same order, but their arrangement in space is different. Their arrangement in a space is different. Maybe they will be having a similar IUPAC names, except for the prefix like cis and trans. These are the diastereomers, which I have mentioned over here. Okay. As I mentioned earlier, the stereoisomers are again classified into two categories, enantiomers and diastereomers. Diastereomers are again classified into a configurational isomers and cis and trans isomers. Here we have taken example of diastereomers, which are also part of a stereoisomers only. So here you can see that we have two compounds which are mirror images of each other. Sorry, not mirror images. These are the mirror images. These are the cis-trans isomers. Okay. This one is a cis-1,2-dichloroethene. This molecule contains two carbons in a chain. Okay. So the parent alkane name will be a ethane, and as it contains a double bond, it is named as ethene. On a ethene, we have two chloro groups at a first carbon and a second carbon. That's why it is named as 1,2-dichloroethene. And as both the chlorines, they are located on the same site. Here it is both chlorine atoms are located on a left-hand side of a molecule, so it will be considered as a cis. While in this molecule, the chlorine atoms are located on opposite side of a carbon. So it will be considered as a trans molecule. The name of molecule will remain same. It is 1,2-dichloroethene only, but just we are adding a prefix cis or trans over here. This is the example of enantiomers. Suppose the carbon is bonded to 4 different atoms. The 1, 2, 3, 4 numbers are given, and these are the two mirror images. Okay, this is the first A molecule, and B is a mirror image of A. So this is again a stereoisomer. Both the molecules are different. They are not same. Their atoms, they are arranged differently in a space. Okay. So both the molecules are a stereoisomers. We'll be taking this enantiomers and diastereomers in detail in later slides. But here you have to remember the definition of a stereoisomers. They are the isomers. Okay, I'm using the term isomer over here because stereoisomers, they are nothing but isomers only. Okay, but just that they have a same connectivity, but the arrangement of atom in a space is different. Okay, they always have same functional groups. You can see that both A and B molecule, they have same functional groups, or either you can consider in this example, both have the chlorine functional groups. Okay, the stereoisomers, they are different compounds that do not readily interconvert. Now you cannot convert this A molecule into a B, or you cannot convert this cis molecule into a trans. You can easily separate them by using different separation techniques. Okay, now in a stereoisomers, we have two parts, enantiomers and diastereomers. So first we are going to study about the first diastereomer part, that is the geometric isomers. Now, geometric isomers, they are formed during the restricted rotation around the molecule. Okay, if the molecule is not able to move freely, then it will lead to a cis and trans isomers. Whenever we have a carbon-carbon single bond, okay, this carbon can freely rotate along this axis. Okay, either it can move clockwise or anti-clockwise. So these atoms which are joined over here, they can change their position in a space with respect to this carbon, because this single bond, carbon and carbon single bond, is free to rotate. So this compounds will not give you a geometric isomers because they are able to freely rotate around the carbon-carbon axis. Say we have a carbon-carbon double bond containing compounds. Now these molecules, they contain one sigma bond and another one is pi bond. Okay. So this straight line, it indicates a sigma bond, and the pi bond is formed by overlapping of p orbitals over here. Now, even if you will try to rotate this molecule over here, say I'm rotating, I want to rotate so that this hydrogen will come on this side and this hydrogen will come on this side. If we want such kind of movement, it will lead to a breakdown of pi bond. It will lead to a breakdown of pi bond. We cannot move freely like a carbon-carbon single bond, because here the carbon is bonded by another strong bond, that is a pi bond. And even if you will try this movement, it will lead to a breakage of a pi bond, which is not allowed over here. It will lead to a instability in a molecule. So there is a restricted rotation around these atoms. We cannot freely convert one isomer into another one. Another example is that we have a closed ring system. Like here we have a 5 carbon containing ring, which is known as a cyclopropane. This is a picture of a cyclopropane only, but it contains a 1,2 dibromo groups on a molecule. Now here, the bromine, both the bromines can be either on the same side of a ring or it can be in a opposite side of a ring. Now here you cannot convert the compound A into a B. For that, if you want to convert, for that you need to break this bond. Okay, the molecule will be broken down, which is not possible here. So the geometric isomers are only possible where there is a restricted rotation in a molecule. Means we cannot move freely the atoms. Okay, that will lead to a geometric isomerism. So we have this molecule 3-methyl-2-pentene. Okay, you can see here that we have a total 5 carbon containing chain, straight chain. Here 1, 2, 3, 4, and 5. So it is named as pentene. Okay, the double bond is present on a second carbon, so it is pent-2-ene, or you can say 2-pentene. On here, it contains a methyl group which is located on a third carbon. So it is named as 3-methyl-2-pentene. Now this molecule contains 2 methyl group on the same site. That's why it is named as cis 3-methyl-2-pentene. We are using cis prefix where the two atoms or two groups are attached on the same side of a molecule. The trans is used when the same groups are located on an opposite side of a molecule. Okay. You can see that this methyl groups, they are located on opposite side of a double bond. So it is said to be a trans 3-methyl-2-pentene. You can note down that the name of molecule remains same. It is 3-methyl-2-pentene only, but we are just adding a prefix cis or trans. Okay. Now another system is also used over here, that is E and Z nomenclature, that we'll be studying later on in our upcoming slides. Okay. This is also named as cis because both the bromine atoms are on the same side of a molecule. And this one is a trans where the bromine atoms are on a opposite side of a ring. Okay. So these are the geometric isomers which are formed due to a restricted rotation around a carbon-carbon bond. Okay, so now we are going to learn about some of the terms. One is the configuration, another one is the stereochemistry. Okay. The stereochemistry is a study of three-dimensional structure of a molecule. It is said to be a stereochemistry. We are going to study about the three-dimensional structure of a molecule. Okay. Suppose this carbon is bonded to four different atoms. So how they are arranged in a space, whether it is in a S configuration or R configuration. Okay, so whether it's a levo or dextro, that will be studying in a detail in upcoming slide. But it's a stereochemistry is a branch of chemistry which deals with the study of three-dimensional structure of a molecule. And configuration is the arrangement of atoms in a space about a chiral center. Okay. The chiral center means the atom or molecule which is attached to a four different groups. Okay. If we have a four different groups, like I have shown over here, the carbon is bonded to a four different atoms A, B, C, and D. They all are different, and this carbon is known as a chiral carbon. This is known as a chiral carbon. Okay. So configuration is an arrangement of atoms surrounding this chiral center. Now here in this case, two kind of configurations are possible. I'm taking a mirror image of this molecule C and B. Okay. Surrounding this carbon, these two carbons, the atoms are arranged in a different order. You can see for that this carbon, the B, is on a left hand side, while in this carbon the B is on a right hand side. So the arrangement of groups surrounding the carbon is different. So we can say that the configuration of both the carbon is different. Okay, configuration is arrangement of atoms in a space surrounding the chiral center. Okay, arrangement of atoms in a space surrounding the chiral center. Here we have a chiral center which is bonded to four different groups. Say the B group here is on a left hand side. In this example, the B group is on a right hand side. So surrounding this chiral center, the arrangement of atom is different for both of these carbons. So we can say that the configuration of both of this molecule is different. Okay. Now, what is the importance of stereochemistry in our day-to-day life or human body or in plants? Now, chirality is phenomena that prevails in the universe. Okay, you can see everywhere the chirality. Even if you will check our hands, they are not superimposable. They are said to be a chiral. You cannot superimpose exactly the right hand with a left hand. So they are said to be a chiral. Most of the molecules that make up the plants and animals, they all are chiral. Okay. Our body contains enzymes, receptors, they all are also chiral. Okay, and the 20 amino acids that exist in a nature, they are also chiral. Okay, and generally all of them are of S configuration. Majority of them are of a S configuration. So whatever the amino acid you will take, whether it's a glycine, alanine, valine, leucine, they all are having a S configuration. All these amino acids are chiral, as well as that they are having a S configuration. Okay. I'm talking about the naturally occurring amino acids. I'm not talking about the synthetically designed or framed amino acids. The molecules of natural sugars are almost all classified as being right-handed, but they are having a R configuration, okay, including the sugar that occurs in a DNA. We have a fructose, glucose, okay, they all are having a R configuration. I'm talking about the sugars which are obtained naturally. They all are of a R configuration. Even our DNA contains sugars, ribose sugar, that is also a R form of sugar. The origin of biological properties relating to chirality means the enzymes, receptors that they are present in our body, they are also chiral. They only bind to a specific enantiomer of the two possible isomers. Okay, suppose you have a molecule, chiral molecule, so that exists in two isomers. One will be a two enantiomers. Okay, so our receptors and enzymes, they are so much specific that they will bind with any one of this enantiomer. They will not bind with both the enantiomers. They will be binding only with the specific enantiomer, either R or S. So here few examples are there related to a biological activity of a molecule. Say we have a asparagine. Okay, this is an amino acid. Here the S enantiomer, it is having a bitter taste, while R enantiomer, it is having a sweet taste. So you can see the comparison over here. We are having both the amino acids over here, S and R, but the S one is having a bitter taste, while the R one is having a sweet taste. We have a DOPA also, that is a neurotransmitter, okay, which is also known as a 3,4-dihydroxyphenylalanine. Here, the S isomer, it is used in as an anti-Parkinson's disease in a drug, as a drug. Okay, while the R enantiomer is a toxic one. Okay, here you can see that we have a chiral center over here. This is a chiral carbon which is attached to a 4 different groups. One is H, NH2, COOH, and methyl group. So these are the chiral centers. So for this, two enantiomers are possible. One is the R and S. The S is used in a Parkinson's disease for treatment, while the R one is a toxic. We have epinephrine. Okay, in this compound also we have a chiral center over here, which is bonded to methyl group, phenyl rings methyl group, OH and H. Same here, we have a chiral center. One of the isomer is a S, another one is a R. Here the R isomer is a hormone which is used in our body, used by our body, and S is a very much toxic to our body. So here you can see that each and every example is having some pros and cons. Some are useful, some are very toxic to our body. Yes. This is a thalidomide drug which was used in a motion sickness during the pregnancy. Okay. It was banned in 1960s or 70s. The child that are born during that period, or the patients who were taken on a thalidomide treatment, their childs were having a sealed limbs or sealed legs. Okay, that was because of the toxicity of this drug, thalidomide's toxicity. Okay, it is well known as a thalidomide disaster. Here, the S isomer of this drug was solely responsible for teratogenic effect, and R isomer was devoid of any side effects. At that time, no one was knowing about these isomers. The R and S isomer was thalidomide, so everybody was using the combination of this. Okay, they were not separating those two isomers, and they were using this drug for a motion sickness during pregnancy. So whatever the childs were born, they were having a teratogenic effect of this drug. They were either having a sealed limbs or sealed legs. So immediately the drug was banned during that era. Later on, the scientists found that the R isomer is totally safe. You can use it for motion sickness. And S isomer, now it is used as an anti-cancer drug. Some researchers are working on that to use this drug as a anti-cancer. So this is a sum up of our stereoisomers. Okay. Stereoisomers, they have identical structures, identical names. Okay. They differ only in the way of atoms are oriented in a space. How the atoms are oriented in a space. That's the only difference over here. They differ in configuration. Configuration, as we have studied earlier, is a three-dimensional arrangement of atoms. So both the stereoisomers, they will differ in their configuration. Their arrangement of atoms surrounding the chiral center will be different. And they will be having the same functional group. Stereoisomers will be having a same functional groups. Like in a constitutional isomers, we could have a different functional groups also. In a constitutional isomers, we have taken example of ethanol, methanol, and a methoxyethane. Here, this one was having a ether functional group, while here we have a alcohol functional group. So here the nature of functional group is also different, but in stereoisomers, always the functional groups are same. Now, to show the stereoisomer on a 2D, on a paper, we are using a different kinds of presentations. One of them is a wedge presentation, another one is a Fisher projection, another ones are Sohor's projection and Newman projection, but these two are mainly used for showing the conformations of alkane. Conformations of alkane. I'm not going to cover this to presentation of molecules. We'll be only covering the wedge presentation and Fisher projection over here. So these presentations are used to show the three-dimensional picture of a molecule on a two-dimension, that is on either on a 10 notepad or in a computer screen. Okay, say we have a molecule like this. This is a tetrahedral carbon. Okay. Now, say this A and B that are attached to a carbon, they are in a same plan. See, they are in a same plan. The C will be going below, beyond or uh, uh, beneath your computer screen or mobile screen. The D will be coming out of the plan of screen. So this bond which are coming out of the plan of screen, they are shown by a solid wedge over here. This is known as a wedge. And the one which is going beyond the screen of your mobile or laptop, it is known as a broken wedge. This is a broken wedge, and this is a solid wedge. Okay. And we all of you know that the bond angle between these atoms, they are 109.5. For all the atoms, the bond angle will be of 109.5 degree. The reason is that this one is a tetrahedral carbon. It is sp3 hybridized. Okay. The same presentation is shown over here. Say these two atoms, they are in the same plan. The chlorine and bromine, they are in the same plan. The one bond will be going beyond the plan of your screen. That is shown by a broken wedge. And the one which is coming out of the plan of screen, okay, that is coming above the screen, it is shown by a solid wedge. So this kind of presentation is known as a wedge presentation. Here you can see this. We have a chlorine and carbon. This is chlorine and this is carbon. Say these are in a plan of screen. The methyl is coming out of the plan of screen, so we will be showing it by a solid wedge. This methyl group. This H and Br, they are going beyond your screen, on the back side of your screen. So we'll be showing that by with a broken wedge. Okay. So this kind of presentations can be used to show the three-dimensional picture of a molecule. It is said to be a wedge presentation. Okay. Here, this straight line indicates that these two atoms are in a plan of paper. The broken wedge, they represent the bond is below the plan of a paper. That means it's going backward. Okay. And the solid wedge represent the bond is coming out of the plan of a paper. Another projection that is used for a representation of molecule, it is known as a Fisher projection. For this, we have to say we have this molecule, which is again a tetrahedral carbon attached to a 4 different groups. Okay, these are the carbon atoms which are attached to a carbon. The bromine and hydrogen, they are in the same plant. The CN and NH2, they are coming out of the plant. Okay, so you have to visualize the molecule from the atoms which are coming out of the plant, from the out of the plant. Say we are visualizing this molecule from here. Okay, the amino is coming out of the plant and CN is going below the plant. Okay, but if you will watch it from this side, the NH2 will be on your left hand side and CN will be on your right hand side. Okay, if you will watch the molecule from this side, between the CN and NH2, between the CN and NH2, we are watching from here. So NH2 will look like on our left hand side and the CN will look like on our right hand side. And this Br will be on upper side and H will be on a bottom side. This kind of projection of molecule, it is known as a Fischer projection. Here, these two bonds are always considered to be coming out of the plane of paper. Means they are coming towards us. And Br and H, they are going away from us, or they are below the or away back side of a screen. So yeah, this is again a Fischer projection which shows this hydrogens, these two hydrogens, they are coming out of the plant. That means they are coming towards us. I can show that like this one. Okay, for atoms or molecules which are coming towards us, we are showing a solid wedge. And these two atoms, this hydrogen and this group, they are going below the plane of screen. So for that we can use a broken wedge. This is a solid wedge which is coming out of the plane of paper, and this is a broken wedge which is going below the plane of paper. So this kind of presentation can be used in a Fischer projection to represent the molecule in a two dimension on a notepad. Okay. I'm not going to cover the Shohorst projection and Newman projection over here because that is solely used for a conformational isomers. Okay. Now we'll be studying about the optical activity. Okay. Now say we have a two enantiomers, two stereoisomers of a compound. Two stereoisomers are there. Okay. One is the dextro, another one is a levo. So when the light passes, the plan polarized light, first let me tell you about the plan polarized light. What is the plan polarized light? The plan polarized light is a light which is oscillating in a single plane. Okay. When we suppose we have a sunlight, so whenever the sunlight comes towards us, its rays are vibrating in all the planes. It will be vibrating in a perpendicular plane, horizontal plane, and all these planes. Okay. The line will be vibrating, the light will be vibrating in all the planes. But when you will pass it through a polarizer, polarizer is the one instrument which will be filtering all the other light rays and will only allow the light which are vibrating in a single plane. So this is a polarizer. Polarizer, the function of polarizer is to filter out the all light which is oscillating in a different planes. It will only allow the light which is oscillating in a single plane. Here it's a vertical plane. Okay. This is the light which is oscillating in all the planes. But here after the polarizer, the light is passed through polarizer. So it is giving us a light which is only vibrating or oscillating in a single plane. This kind of light is known as a plane polarized light. Now when this plane polarized light is allowed to pass through stereoisomers, they may change the angle of plane polarized light slightly, either on a left hand side or right hand side. This is the right hand side and this is left hand side. So here you can see that this plan polarized light was always oscillating in a straight plan, but it was allowed to pass through a container which was containing our optically active molecule or stereoisomer, and it has changed its angle of rotation. You can say that after passing through a sample, its plan has been twisted on right hand side. So this kind of compounds which rotate the direction of plan polarized light, they are known as optically active molecules. Okay, if they are rotating the plan polarized light on the right hand side or clockwise, it is said to be a dextrorotatory. And if they are rotating the plan polarized light on a anti-clockwise direction, they are said to be a levorotatory. Okay, this one is an example of dextrorotatory where the light path has been changed to a clockwise. Instead of a straight one, it has been slightly twisted on a clock side. So it is a dextrorotatory compound. If it is like this, incident radiation was like this, and has been changed on a anti-clockwise direction. This kind of compounds which change the plan polarized light on the left hand side, they are said to be a levo compounds. So now we come to a chirality concept. So everything that is present surrounding to us, many of the things they are chiral. The examples are our hand. You cannot superimpose your left hand on a right hand. That is a chiral molecule. Suppose you have a bike key or you have a socks. You cannot place your one sock with the another. That is again show the chirality. Okay. So it is a property of a handness. Okay, you cannot superimpose left hand on a right hand. That considered as a non-superimposable. Similar to that, our organic molecule also shows the chirality. Okay. Some of the organic molecules which contain chiral center, the carbon which is bonded to a 4 different atoms, they also show this kind of property of handness. Here we have an example of these two molecules. Okay. Say on a chiral center or free atom, carbon atom, we have a methyl group. Here also we have a methyl group. Here we have a bromine. On this side we have a ammonia. Okay. We are taking a mirror image of this molecule. This molecule is completely a mirror image of this molecule. Okay. The CH3 versus CH3, this CH3 versus this CH3, bromine, bromine, ammonia, ammonia. Now, if you will try to superimpose these two molecules, if you will try to overlap these two molecules, it will be completely overlapped. And this kind of molecules which can superimposed on their mirror images, they are said to be achiral. They are achiral. The reason is that they do not contain chiral center. Here, the 4 different groups that are attached on a carbon, they are not different. Here you can say that 2 methyl groups are identical. Because of that, their mirror images are superimposable. Now we have another molecule over here in which I have added 4 different groups on a carbon: CH3, Cl, Br, and NH3. We are going to take a mirror image of that. Okay, Cl versus Cl. The methyl is away, so this methyl is also away. Now, if you will try to superimpose these two molecules, okay, you can see that the Cl will be superimposing on a methyl group, and this Cl will be superimposing on this methyl group. So they cannot be superimposed on each other. This kind of compounds, they are said to be chiral. They are showing a property of handness. They are not superimposable on that mirror image. The reason is that the carbon is bonded to 4 different atoms. So this kind of molecules, they are said to be a chiral molecules. So a molecule with no stereogenic center, no chiral carbons, okay, it will be a achiral. Okay? In general, the molecule which do not have a chiral center, like in the first example, this molecule do not have a chiral center, it is achiral. So in general, the molecules with no chiral center will be a achiral. Okay. The exceptions are there, which is a molecule. Some molecules contains a chiral axis, like biphenyls. Okay. Biphenyls are there, or allenes are there. These are the molecules which do not contain chiral center, but they will still show you a chirality. Okay, these topics are generally covered in a post graduation courses. So I will be skipping this. Okay, some molecules contain chiral axis, like we have a biphenyl, spirans, allenes. They do not contain chiral center, but still they will show you a chirality. But we are not going to detail of these molecules. Suppose one molecule contains a one chiral center, so it will be definitely a chiral. If single chiral center is present in a molecule, it will definitely be a chiral. If two or more stereogenic centers are present, if two or more chiral centers are present, the molecule may or may not be chiral. Okay, suppose a molecule is having a two chiral centers. Okay, so I have the different groups over here, A and B. Here also B and A. These carbons, they contain, they are the chiral carbons. But overall, this molecule may or may not be a chiral. Okay, it could be a meso compound also, that we'll be studying in upcoming slide. Okay, this is there in a presentation. We'll be discussing that. So achiral molecules usually contain a plan of symmetry, or they contain a plan of symmetry. Sorry. So achiral molecules which contain chiral center. Okay, but overall they will not show you a optical activity because they contain a plan of symmetry. The most common feature because of which the molecule will show you a chirality is a chiral center or asymmetric carbon. Okay, generally the compound which is having a chiral center or asymmetric carbon, they will generally show you a chirality. Chirality means, chiral center means the carbon which is attached to a four different groups. So we'll be studying this now, enantiomers and element of symmetry now. Okay, now here you can see that this carbon is bonded to a chlorine, bromine, iodine, and fluorine. All are four different groups. So this carbon can be considered as a chiral carbon or asymmetric carbon, or you can say it's a stereogenic center. Here also we have a carbon which is attached to a four different groups. Here we have ethyl, propyl, bromine, and hydrogen. Even in this case, all the four groups are different. So this can also be considered as a chiral center or asymmetric center or stereogenic center. Now, what is the element of symmetry? Some molecules, they are having a chiral center also, but still they will show you a optical inactivity. The reasons are the plan of symmetry or center of symmetry. So we'll be studying about this element of symmetry now. First, we'll be focusing on a plan of symmetry. So what is plan of symmetry? It's a mirror plan that cut the molecule into a two equal half. And one of the half is superimposable on its second half. Okay. Here we say we are having this molecule and we are going to cut this molecule into a left hand part and a right hand part. Here the left hand part will be superimposable, or it will be identical to a right hand part. This kind of molecules which show this kind of identical parts, they are said to be having a plan of symmetry. Okay? Here we are able to cut this molecule into two equal halves which are mirror images of each other. Okay, you can see that we are having a half green, hydrogen over here, hydrogen over here. This is say oxygen. Oxygen is divided into two parts. So this molecule can be cut down into two equal halves and they are mirror images of each other. So this is said to be a plan of symmetry. Say we have another molecule which are having four different groups. Here these two groups were same. Now this molecule is having a four different groups. If we cut this molecule into a two equal half, these two portions, left portion and right portion, they are not the mirror images of each other. It is said to be it is said to be it do not have a plan of symmetry. It has no plan of symmetry. It's a chiral carbon, okay, and the half which are generated left hand half and right hand half, they are not identical to each other. So this kind of molecules are having, they do not have a plan of symmetry. Now next we'll be moving to another examples. So we have a molecule, this is a 2-chloropropane, you can say. This one is containing a 3 carbons, 1, 2 and 3. It's a propane molecule. On the second carbon we have a chlorine. If we will divide this molecule into two equal halves, this portion and this portion, they are identical. They are mirror images of each other. You see that we have a methyl group, methyl, both are same. So it have a plan of symmetry and it is said to be a achiral. Say we have another example. It is 2-chlorobutane. It is said to be a 2-chlorobutane. We'll draw the structure of 2-chlorobutane first. We are focusing on a second carbon only. So I'm drawing the hydrogens around that only. Say this is a 2-chlorobutane. If I will convert or cut this molecule into two halves, will that be identical? No, because here we have only one carbon, while here on this side we are having a two carbons. So it doesn't have a plan of symmetry. This molecule doesn't have a plan of symmetry, and this is said to be a chiral. You can see the molecule, same molecule over here. It is having a methyl group on this side and ethyl group on this side. It's 2-chlorobutane. It is a chiral molecule. Now next one is the center of symmetry. What is the center of symmetry? Okay. Now if you look at these molecules, okay, if we draw a imaginary center over here, and we will be drawing a imaginary line between the molecule. Okay. Now here, at the same distance from a center, we are getting two identical atoms. Here also we have a chlorine, here also we have a chlorine, here also we have a hydrogen, here also we are having a hydrogen. We'll draw another third imaginary line. At an equal distance, we'll be having a two fluorine atoms. So it is the point in the center of a molecule. We have drawn all this line from a center of a molecule, to which a line can be drawn from any atom such that when extended an equal distance on opposite side, the line meets another atom of a same kind. Okay, here we were having a chlorine and we are drawing a exact opposite line at an equal distance. We are getting another atom which is of a same type, same kind. So this is said to be a center of symmetry. Here we are drawing another line from fluorine. Say this is a distance, x distance. So we have to move x distance on an opposite side. We should get a same atom over there. And this kind of symmetry is said to be a center of symmetry. It doesn't have a plan of symmetry, it is having a center of symmetry. Okay, if you draw the plan over here, say I'm drawing a plan over here, I'm going for a plan of symmetry over here. Here I am having a methyl and chloro on upper side, and the chloro and methyl on opposite side. So they do not, it is not said that it is having a plan of symmetry. But whenever we draw a line passing from a center of molecule, we are getting the same atoms and opposite side. So this molecule is said to be having a center of symmetry. So I hope it is clear that the difference between the plan of symmetry and center of symmetry. So the molecules which have a symmetry, they are generally achiral, and the molecules which do not have a symmetry, either a plan of symmetry or center of symmetry, they are generally chiral molecules. Achiral molecules, these are the compounds which have no chiral centers. Okay, you can see that this compound is having a methyl groups. It is not attached to a four different groups. We have a chlorine and bromine as a different atoms, but these two methyl groups are identical. So if you will take a mirror image of this one, it will be a superimposable. It will be a superimposable, or you can say that it is having a plan of symmetry also, or a center of symmetry also. So these molecules, they are achiral molecules, and they are always optically inactive, means they cannot rotate the plan polarized light. Okay, now this stereoisomers, they are classified into a enantiomers and diastereomers. So we are going to start with the enantiomers now. Okay, stereoisomers, they are classified into enantiomers and diastereomers. So enantiomers, they are the compounds with the same molecular formula, same connectivity, but different arrangement of atoms in a space. Okay, they have a same molecular formula, same order of connectivity, but they have a different arrangement of atom in a space. Focus on these two molecules. Their molecular formula will be same because they have a same number of groups. Okay, the same groups are present over here, so their molecular formula is same. Their order of connectivity, that means this carbon is bonded to chlorine, hydrogen, methyl, ethyl. This carbon is also bonded to similar functional groups, so order of connectivity is also same, but the arrangement of these groups in a space is different. Okay, here you can see that this ethyl group is located on a right hand side of a molecule. Here it is located on a left hand side of molecules. So the group are arranged in a different order in a space. So this kind of molecules, they are said to be a enantiomers. They are the stereoisomers which are mirror images of each other. Enantiomer definition શું છે? It's a stereoisomer which are mirror image of each other. They are said to be enantiomers. They have generally one chiral center. They lack plan of symmetry. They do not have a plan of symmetry or center of symmetry, and they are non-superimposable on mirror image. If you will try to superimpose this molecule over here, they are not superimposable. Okay, so the definition of enantiomers can be said as they are the stereoisomers which are non-superimposable mirror images of each other. Which are non-superimposable mirror images of each other. Here you can see that I have tried to superimpose these two molecules, but here they are not exactly superimposing on each other. They are not identical. They are different. So they are said to be enantiomers. Now these are the different properties of enantiomers. The enantiomers, they have a same physical properties. Physical properties like we have a boiling point, melting point, refractive index, solubilities. They all are considered as a physical properties. Now for enantiomers, we have same physical properties. Okay. Nidhi, can you tell me how much time do we have completion of this?
Sir, we have to complete it at 11 o'clock.
Okay, but I hope that this will not be possible to complete all the topics over here. Like diastereomers will be left as such. Will I go
Okay,
fast?
sir. Yes, sir. Just give the base introduction of diastereomer.
Okay, thank
Okay,
you.
sir. Huh.
Okay, so these are enantiomers. They do have a same physical properties, but their reactivity, their chemical properties will be different. The reaction with chiral compounds will be different. If you are going to react your enantiomer with a chiral reagent, the reaction will be a different. Okay. Not mirror images of each other. So we have this cis molecule and trans molecule. They are having the same molecular formula, same order of connectivity. The carbon is bonded to methyl group, hydrogen. This carbon is also bonded to methyl and hydrogen, but their arrangement in a space is different. This methyl group is trans over here. Okay. So if you try to check that whether they are mirror images of each other or not, they are not the mirror images. So it is said to be a diastereomers. So diastereomers are the stereoisomers. Here we have to use the term stereoisomers. Stereoisomer means they have a same molecular formula, same order of connectivity. Okay, but they are not mirror images of each other. They are said to be a diastereomers. This is another example of diastereomers. We have a OCH3 fluorine. They're on opposite side. Here they are on the same side. So these are the diastereomers. Again, they are not mirror images of each other. So we have another diastereomer pair also over here. In this molecule, we have two chiral centers. These two are the chiral centers. We have a COOH, NH2, H, and this group. If we'll take another molecule which are having a only configurational change on this below portion, you can see that the upper half is remains same. Upper half this molecules, they are identical, but there is only configuration change on the lower half. Okay. Here the OH is on our right hand side, here the OH is on our left hand side. So this two molecules are not mirror images of each other, because the upper portion is mirror image, but the lower is not, sorry, the upper portion is not mirror image, but the lower one is a mirror image. Okay, but if you focus as a molecule, complete molecule, they are not mirror images of each other, and this are again are diastereomers. So diastereomers are the stereoisomers which are not mirror images of each other. Okay. Now they are having a different physical properties, unlike the enantiomers. Enantiomers are having a similar physical properties. The diastereomers, they do have a different physical properties. Okay, you can see here that they have a different physical properties. So this is the difference between enantiomer and diastereomer. Both have a same carbon, same connectivity. Here enantiomers, they are mirror images of each other. These are not mirror images of each other. These are non-superimposable. These are also non-superimposable. All the configurations are opposite. Generally, whatever the suppose in an enantiomer we have a one chiral center. So in another enantiomer, the configuration will be opposite. In diastereomers, we do have a two chiral centers. Two chiral centers are there. This may have a same configuration. Say this one is in R configuration, this is also in R, but this configuration of the next carbon will be a different. Okay, the configurations are different over here. Okay. Yes, and one more thing, a meso compound. This molecules, yes. Okay, just a minute. Let me complete this meso compound and then I will be finishing my presentation. Okay. These molecules, yeah, these molecules are enantiomers. They are mirror images of each other, but they have a plan of symmetry. They have a plan of. They have a plan of symmetry. You can see that we have OHOH, COOH, and H and H on the opposite side.
Yes,
So this,
Renu, just turn off your microphone.
so they have. Okay. Nidhi, if you can mute her mic.
કઠોળી દવા ત્યાં ઝાડા જરાક વધારે કરે તો દવાથી પાછા ઝાડા થાય કફની દવાથી
This molecule is having a plan of symmetry. So this is said to be a meso compound. Even if they contain a two chiral centers, they have a plan of symmetry. So this overall molecule becomes a chiral. Here you can see that they have a plan of symmetry. So this kind of compounds they are said to be meso compound, and meso compounds they are achiral molecules. They are achiral. Okay, so I'm stopping my presentation over here. The RNS nomenclature I could not cover because of the time constraint. Sorry for that. Thank you, ma'am. Over to you, ma'am. Nidhi, ma'am.
Thank you so much, sir. Sir, it was very informative session. Thank you, sir. And if any participant has any doubt regarding this, please ask the question or write down in the chat box.
Okay, thank you. I'll be ready to answer that if any doubts are there.
Thank you, sir.
Okay.
Sir, please.
I will be sharing my presentation with you later on, today only, ma'am.
Okay, sir. Yes. Sir, as a token of appreciation, I would like to facilitate with e-certificate on the behalf of Parul University. So please accept it.
Yeah, thank you, madam. Okay, thank you. Thanks a lot,
Sir,
ma'am.
Sir, please just close your presentation.
Oh, sure, ma'am.
Okay. Okay, thank you, sir. Sir,
Thank
this
you.
is the certificate.
Yes, ma'am. Thank you, ma'am. Thanks a lot to all of you, ma'am. All the organizing committee and Parul University. Thanks for inviting me for a lecture on stereochemistry.
Thank you, sir.
Thank you from School of Pharmacy also. Very nicely you have covered the topic. Very exhaustive. Thank you.
Thanks a lot, ma'am.
All the participants will receive feedback form link, and all of you need to fill it. Okay. I'm just sharing the. I have just shared this link also, feedback link. So please do the fill it. So thank you everyone for presenting here. Thank you so much.
Okay, thank you, ma'am. Shall I leave, ma'am? Okay.
Okay, sir.
Okay.
Yes, sir.
Thank you. Thanks, ma'am.